which you have done before, but I start out with polynomials because the rest of chapter 3 kind of extends all of these ideas and talks about all different types of polynomials, so we're kind of leading into that. So first we have to write out what a polynomial is. So it's kind of a fill in the blank. You've got a box at the top. And it tells you a polynomial function of degree n just has to be a non-negative integer, is of this form. So that's what you want to put on that line here. The a's are just coefficients, so they're just numbers. Your powers have to be whole numbers. So your powers on x are like 0, 1, 2, 3, and so forth. So first example, we just want to look at some polynomials, and I want to find the degree, leading coefficient, and constant for each of these. So do you guys remember what all these terms are? The degree, let's fill in these blanks then. Your degree is the highest power of x. It does not necessarily have to be the first one you see. A lot of times it is because that's standard form. But if I see an x to the 5th plus a 7x to the 10th, 10 is my highest power, so that's my degree. Okay, so it doesn't have to be the first term. Then, what's our next term on here?
Leading coefficient.
So the leading coefficient is the coefficient on the term with the highest degree. So again, that might be your first term, but it might not. Your terms are separated by the addition and subtraction sign, so you're looking for where do I have my highest power of x, and the coefficient on that is my leading coefficient. All right. What is a constant?
Just a minute.
Constant is just a number without a variable. So knowing what these terms are, let's take some polynomials and pick out each of these things. So degree, that's the highest power. So in this case, it's just a 1. My leading coefficient, you take that term with the highest degree and you're looking for the coefficient on that, so it would be 5. My constant is just the number without a variable, so that would be -1. The next one. On a polynomial, the powers have to be nice, 0, 1, 2, 3, 4, but your coefficients can be anything. So it's okay that I have a radical here because my variable isn't under the radical. My degree, the highest power of x I see is 4. So the leading coefficient, the coefficient on that term is just a 1. And the constant, there we don't have one, so that would be a 0. There isn't a term without a variable here. Next one, what would be my degree on this? 3. You notice it's not the first one, but the highest power of x I see is right here. So the degree is 3. leading coefficient of that term is -1/2, and my constant is a +5. Any questions on that? If you just have f of x equals 0, that is what is called the zero polynomial. And we say that has no degree. The reason 0 is the same as 0x, which is the same as 0x squared or 0x cubed or whatever power I want to put. And so I can't list the degree because it could be a degree of 0 or 1 or 2 or 3. I could put x to any power with that. So we say in that case it has no degree. Now if I say f of x equals any other number, for instance 3, 3 is only the same as 3 times x to what power? What power would make that x go away? A 0. So if it's equal to any other constant, it has a degree of 0 because it has to be an x to the 0 with it. But just f of x equals 0, we can't pick out the degree. Alright, the rest of the day today we're talking about a specific type of polynomial, the quadratic. So what do I mean when I say a quadratic? It has an x squared, so it's like your ax squared plus bx plus c. Your function is equal to that. When you graph these, what does a graph look like? Parabola. We've already seen that. We use that as a parent function. So that's not a surprise to us. When you graph it, your parabola can open up or it can open down, depending on your coefficients. That's how we decide if it has a maximum or a minimum point. If your parabola is opening up, this is what? A maximum or a minimum? That's a minimum. If your parabola opens down, then you have a maximum. What is another name for that highest or lowest point on our parabola? If you draw the vertical line going through the vertex, we did this in Algebra 2 when you graphed quadratics. You drew it as a dashed line. Do you remember what we called that?
Line of symmetry.
The axis of symmetry. It is a line of symmetry. We just typically say axis. So the axis of symmetry is the vertical line that goes through the vertex. Basically, if you fold your graph on that line, it will overlap itself. All right. Any questions so far? So let's talk about how we can graph these. Standard form for a quadratic is what we already wrote down, the ax squared plus bx plus c. That's not the best form for graphing. Do you guys remember talking about vertex form last year at all? So vertex form is nicer for graphing. In that, your vertex is the ordered pair HK, which we will talk a little more about in a few minutes. And the nice thing about this, if you have the vertex form, then you can use transformations to graph it. You know, your H will move it left or right, K is going to move it up or down, and that A in front is stretching or shrinking. So that's why we prefer the vertex form, then we can use stuff that we've already been practicing, the transformations, to get our graph. Alright, so let's practice. We're going to graph a few. We know we should be getting a parabola. We're going to graph these and give the domain and range. This first one, I'm trying to illustrate a point here, so I want us to graph this by plotting points. We're just going to make a t-chart until we get the graph. So give me a number. What can I plug in? So if I put in 0, I get 0 minus 4, so negative 4. If I put in a 1, 1 squared is 1, 4 times 1 is 4, minus 4, and we get 1. What do you want to plug in now? Okay. Negative 1 squared is 1, 4 times negative 1 is negative 4, minus 4, and we get negative 7. Do I have enough to draw my graph yet? If it were a line, yes, but we're looking for a parabola, right? Have I found the point where it bounces back and starts repeating itself? No, so we need to keep going. What do you want to plug in now? So negative 2 squared is 4, 4 times negative 2 is negative 8, minus 4, and we get negative 8. Is that enough? Nope. We still need more. So if we did negative 3. Negative 3 squared is 9. 4 times negative 3 is negative 12. Minus 4. And we get negative 7. Is that enough? Yes. What we can see now is it started repeating itself. At negative 2, negative 8, that's my vertex, so that's the line of symmetry going through it. If you wanted more points, you talked about in algebra 2 how everything can be reflected across that line. So my point 0, negative 4, if I flipped it across, go here. If I reflect this one, it goes here, and that gives me a few more points so we can actually see our quadratic. So we've got the graph. Why is this not the best option for graphing? Takes a lot of time. We had to find our vertex and find when it bounced back. Now we were able to do it because my vertex was a nice number, but what if the vertex had been at negative 1/8? Would you have just thought to plug in negative 1/8? No. So it leaves a lot of room for error. So this is not what we really want to do. It just takes too much time. Domain and range. Yep. As this quadratic goes, it's just going to keep spreading out, so it'll extend left and right. So eventually you hit everything. Your range is talking about your y. So I said go from the bottom up. So if I'm coming from the bottom, the first thing we hit is negative 8. We'll get a bracket, and then it just keeps going up forever. So negative 8 to infinity. Alright, so let's try one using a different option. We don't like this plugging points. What else can we do? We've done problems like this before when we just did transformations. We had to plot our parent function. I still expect that. So minimum of 3 exact points if you do a parent function. 0 squared is 0, 1 squared is 1, negative 1, 1. I already have the graph here, so let's go ahead and do 2, 4, and negative 2, 4. So there is my parent. And you draw that in as a dashed line. What does a negative do? It's out in front, so we'll flip everything over the x. And what is that 2? Another way to think about it, outside is y and it does what it says. So this has multiplied by negative 2 on the outside. So we're really just taking all of our y's times negative 2. So here's a y value of 0. times negative 2 is still 0. Y value of 1 times negative 2 is negative 2. Y value of 4 times negative 2 is negative 8. Same thing over here. So what happens is we have a skinny upside down parabola. Oops, hopefully your graphs are a little prettier than mine. Domain. Every quadratic, as time goes on, it just keeps getting wider, so eventually you hit everything. Range is referring to your y, so you go from the bottom up. This is going down forever, so you're coming from negative infinity. Stops right here at 0. You hit the 0, so it gets a bracket. Okay, once you guys do this one, graph the parent function, the transformation, and give a domain and range. So parent function, anytime I ask you to graph something with transformations, I give you a point for doing the parent function. So you have to do that part. Then, what's my minus 3 doing? And the minus 1, down 1. So if I go right 3, down 1. Minimum of 3 points, but you can always do more. If I asked you guys some questions, what's the vertex of this? 3, negative 1 is the vertex. What's the axis of symmetry? But it's a line, so you have to write it as, yes, so our vertex is 3, negative 1. The axis of symmetry would be x equals 3. Can you tell me the x-intercepts?
2, 0.
Yeah. You could either list them, or if you did the order pairs, 2, 0, and 4, 0. Y-intercept, if I extended my graph out that far, yeah, we're hitting it at 8. So I could ask you questions about this. Domain and range, domain is? Range would be? So if you had the graph, could you look at it and answer some of those questions if you were asked? So let's talk more about what to do if it's not written in the vertex form. So if I give you the original in vertex form, it's no big deal to do these transformations, but it's not always going to be written that way, and we would like it to be so that we could easily graph it. So we have some different options. In Algebra 2, what you usually did is just found the vertex, and Ms. Keller would have you find the vertex and the y-intercept and the axis of symmetry and get your points from there. If we just wanted to find the vertex, to find your x value, does anybody remember what you do? If it's in the vertex form, it's hk. If it's just written in standard form, ax squared plus bx plus c. Well, so the x value of the vertex is the same as the axis of symmetry. So this gives you the axis of symmetry and the x value in the vertex. To get y, all we have to do is plug in x. So that is the equation of the axis symmetry. How do you find a y-intercept? What is a y-intercept? What does that mean? Where you touch the y-axis, and if you're on the y-axis, what's x? So you plug in a 0 for x and you get your y-intercept. Okay, so let's use that to graph some of these. So I'm asking vertex, axis of symmetry, y-intercept, domain and range, and graph on all of these. First thing we have to do, opposite of b over 2a. So my b is 2, a is 1. So I get negative 2 over 2, which is negative 1. Then what do we have to do with that? Mm-hmm. So that means my vertex is the ordered pair, negative 1, negative 6. Then the axis of symmetry is just a vertical line, so it's x equals the x value of the vertex, so x equals negative 1. When you graph that, you just put a dashed line for that axis of symmetry. It's not technically part of the graph of the parabola, it's just there to help us get our graph. Okay, then y-intercept, how do we find that? Plug in a 0 for your x, and you get negative 5. So we hit the y-axis at negative 5. You have to have 3 points for the graph. I only have 2 so far. How do I get my third? We know we're symmetric across the y-axis, or across the axis of symmetry. So this is 1 unit away, so if I reflect it, it goes 1 the other way. That gives me my 3 points, which is all I need for my graph. Now if you wanted more, you just have to plug in another x value to get another point.
Do we have to do the pair function?
No, because we didn't use transformations to get there. We just used our vertex formula. Alright, so domain. Every single quadratic, that domain will be the same. My range, my graph starts down here at negative 6, so that's a bracket on my negative 6, and goes up forever. So negative 6 to infinity. Do just a little more and then we're going to stop for today. So this one, find my x value vertex opposite of b, so my b is 8 over 2 times a is negative 2. That gives me a 2. To get your y, you have to plug that in. Oh, I skipped the middle one, didn't I? Sorry, this is C. I didn't vertex is 2, 5. Axis of symmetry is x equals 2. Y-intercept, if you plug in a 0 for all of your x's, we get, so if we plot all of this stuff, can you tell by looking at this equation if your parabola is going to open up or down? That A decides which direction it's going to go, and we can also see that from our points. So then if I reflect my point, my y-intercept, domain is always the negative infinity to positive infinity. The range would be, I skipped B. I want you guys to go back and do that one. Let's check this and see how vertex is at 1, 4. For axis symmetry, x equals 1. Y-intercept is 7. So that allows you to get your graph. Domain is always negative infinity to infinity. This one, it's opening up, so your range is 4 to infinity. Are we good? We will finish this note